NASA's strategy involves establishing a lunar base as a precursor to Mars missions, streamlining the process of reaching the Red Planet. Elon Musk, the founder of SpaceX, is fervently leading his own charge towards Mars, while European and Russian space agencies also express ambitions for human missions. However, the real challenge lies in sustaining human life on the inhospitable Martian terrain. In stark contrast to Earth, oxygen is not the primary life-supporting element on Mars. This prompts the question, how does NASA plan to generate oxygen on the Martian surface? Furthermore, exploring the oxygen production methods on the International Space Station, ISS, raises queries about their adaptability to Mars and the unique challenges posed by the Martian environment. Join us once again at Infopedia Hub as we delve into the multifaceted reasons driving humanity's desire to inhabit Mars. Scientific exploration and space curiosity play a role, but there's also the underlying concern that Earth could face catastrophic events akin to the extinction of dinosaurs 6.5 billion years ago, or the current specter of climate change. This sense of urgency propels Mars into the forefront of human colonization efforts. Elon Musk's initial goal of establishing a Mars colony by 2026 has now been revised to a tentative 2029 prediction. The aspiration to place the first human on Mars is set for realization by 2029. Mars shares several characteristics with Earth, including a day length only 39 minutes longer, diverse weather conditions, and polar ice caps. However, the key challenge is the scarcity of oxygen, a fundamental requirement for human survival. The task at hand is not merely producing oxygen for a few individuals, but sustaining an entire Martian colony. Drawing inspiration from the International Space Station's 25-year legacy of maintaining life support in harsh space conditions, the focus shifts to the monumental task of generating sufficient oxygen on Mars. The ISS currently caters to the daily water needs of 4 to 5 astronauts, totaling 45 liters a day, 1,350 liters a month, and a staggering 16,200 liters annually. The journey to Mars is undoubtedly a pioneering venture, necessitating innovative solutions to address the formidable challenges posed by the Red Planet's environment. Apart from this, the ISS utilizes 1,000 kilos of oxygen gas annually. The question arises, how is such a substantial amount of water and oxygen produced in a space station located 400 kilometers away from Earth? This feat is achieved through the collaboration of two systems within the ISS, the Water Reclamation System, WRS, and the Oxygen Generation System, OGS. To implement these systems on Mars, it is crucial to comprehend their functionality. The Water Reclamation System collects water from human waste, such as urine, sweat, or humidity. This system processes the collected water, making it drinkable. The WRS collects existing water in the ISS, purifies it, and ensures 98% of water is reused, reducing waste. Adjacent to the WRS is the Oxygen Generation System, which extracts a small amount of water from the WRS and subjects it to electrolysis, a process familiar from 5th grade science class. Electrical current passes through water, converting it into oxygen gas and hydrogen gas. While the oxygen is crucial for breathing, the hydrogen poses a risk as a flammable gas. However, it is not wasted. Instead, it is directed to the Sabatier system. This system combines the waste carbon dioxide from astronauts with hydrogen to produce water, methane gas, and a modest amount of heat. While the water is reused and the heat is managed within the system, the methane gas is expelled into space. This decision is based on the necessity of oxygen for processing methane, and oxygen is a critical resource on the ISS. Despite the 98% efficiency, there are still losses and leakages in each system. Consequently, every 6 months or a year, water and oxygen are replenished through costly refueling missions from Earth. The expense of delivering just 1 liter of water to the ISS, situated over 400 kilometers away, exceeds $2,500. Therefore, this method used to generate oxygen on Mars, which is 22.5 kilometers away from Earth, is not cost-effective. It is imperative to design a system that utilizes Mars's existing resources to produce oxygen. In 2021, NASA's Perseverance rover carried out a significant experiment with the installation of MOXIE, Mars Oxygen In Situ Experiment. Unlike the ISS, where water is refueled, finding water on Mars requires exploration of polar caps or drilling beneath the surface to extract ice. This is why MOXIE utilizes carbon dioxide from the Martian atmosphere to generate oxygen. In simple terms, 95% of Mars' atmosphere is composed of carbon dioxide. MOXIE extracts carbon dioxide from the external atmosphere, pressurizes it, and then channels it into an electrolyzer heated to 800 degrees Celsius. This high temperature separates oxygen gas from carbon dioxide. The electrolyzer is crafted from gold due to its excellent heat conductivity, protecting other components of the Perseverance rover from the intense heat. However, this process not only yields oxygen, but also carbon monoxide. The drawback is that if carbon separation is incomplete, it can form a carbon layer, potentially damaging the rover. Consequently, the procedure is executed with great care. Yet, how much oxygen can MOXIE produce on Mars at a given time? The process demands substantial energy, prompting NASA to activate MOXIE selectively when energy is conserved from solar panels. To date, MOXIE has produced a mere 122 grams of oxygen, sufficient to sustain a person for only 3.5 hours. Scaling up oxygen production on Mars through MOXIE requires a larger version of the device and a significant power plant, presenting a formidable challenge. It is crucial to recognize that MOXIE initially compresses carbon dioxide with a compressor before subjecting it to the 800 degrees Celsius heating. Both processes demand considerable energy. Scientists are actively exploring a future technology wherein carbon dioxide molecules can be disassembled at lower temperatures through vibration, eliminating the need for intense heating. While this technology has been tested in the lab, conducting experiments on Earth is challenging due to its high atmospheric pressure and temperature. Mars' atmospheric conditions, however, make it an ideal environment for such technology. Regardless of the technology employed, the ultimate goal is to produce oxygen using resources available on Mars. The device responsible for oxygen production should not rely on Earth, as the International Space Station ISS is only 400 kilometers away. In the event of a malfunction in the ISS oxygen generation system, astronauts have the option to return to Earth with emergency suits and a brief wait for refueling. However, on Mars, after colonization, a malfunction in the oxygen generation system poses a more significant challenge with no refueling option, making the return journey to Earth much more complex. We appreciate your support and encourage you to like and share this Infopedia Hub video. Thank you for your valuable comments, and we look forward to bringing you more insightful content in our upcoming videos.